Welcome to another series of Learning with Pete. This is Learning with Pete, and I'm your favorite teacher, Pete. Today, we are going to be talking about dimensional analysis, also popularly known as dimensional method. Dimensional analysis is a very powerful and yet very simple tool that a lot of scientists, physicists, and even mathematicians use in problem solving. Big science organizations such as NASA, SpaceX use them a lot, and at the end of this series, we will be using them too. So now, let us delve deeper. So our very first question obviously is going to be, what is dimensional analysis? Dimensional analysis in its simplest form is the study of dimensions of physical quantities. If you think about what I just said carefully, then you can correctly say that all physical quantities have dimensions. Notice, however, that I said all physical quantities and not quantities. In science, there's a difference. For example, mass is considered a physical quantity in science, but money, though it's a quantity, is not a physical quantity. Okay, to have more insight into what physical quantities are and how they are defined in science and there are differences between the difference between physical quantities and quantities, you can check out our video series on unit and measurement. Link is posted in the description below. Another very good example to illustrate this point is to consider the quantity angle. Angles are quantities that seek to measure the amount of space wherever two or more lines meet. The unit of the angle is the radian. However, inside angles, though quantities are not considered physical quantities and so do not have a dimension. That also means that one way to differentiate between physical quantities and any other quantity is to check whether the same quantity in question has a dimension. We'll delve more into that in this week, but for now, let's try to understand what dimensions themselves really are. Dimensions are quite technical and may be a bit elusive to understand. And so in order to understand what they are, let's just first try to understand what they are not by first looking at this example. So I'll try to illustrate that with this example on the board. So here on the board, you will see a physical quantity and then its unit. So the mass here is a physical quantity, an SI physical quantity, fundamental physical quantity for that matter, and this is its unit. Okay, we are already familiar with this from our previous lessons. We are familiar with this physical quantity and this unit, but then what is this? Okay, so this is a dimension of mass. The concept of dimensions is a bit technical. Okay, so it's a bit, like I said, it's a bit elusive to understand, but then I'll try to do my best to explain it to you. So here's the physical quantity, and here's the dimension of the physical quantity. The dimension of the physical quantity is illustrated by putting that physical quantity in a square bracket or by representing the dimensional symbol. So this is a dimensional symbol for mass. So if I want to write show the dimensions of mass, I write mass and put in a square bracket or write this symbol M here. Are we okay? So this is the physical quantity. This is dimensions written in square brackets, and this is dimensional symbol. And this is the unit and its symbol. So another example would be, let's say, length. The dimensions of length will be written like this, and then the dimensional symbol for that is a capital L. And then the unit for the length is the meter, the SI unit. Time too. So time. Dimensions of time, T. The unit is the second. S. So temperature. Dimensions of temperature. And then theta, and then Kelvin, K, and then we are giving the amount of substance. So these quantities are basically four fundamental quantities on the board. Okay, and these quantities have dimensions. And the dimensions report are fitting the square brackets. Like I said, if you want to show that a quantity has dimension, you want to show the dimension of a physical quantity, just write the name of that physical quantity and put it in a square bracket here, as here. Okay, or you present it with a dimensional symbol. So if you take mass, if you want to show the dimension of mass, you use M. Is that okay? If you want to show the dimensions of time, you use capital T, you use capital L. Even amount of substance has dimensions. Electric charge also has dimensions, but sticking to our high school scope of science, okay, or syllabus, we are only going to look at these 4 fundamental dimensions. Okay, they are fundamental quantities, so their dimensions are also called fundamental dimensions. So now back to our school of thought, or our train of thought that we started before this example scheme. So with these examples, we can understand what dimensions are not, or what they really are with this example. So from this we can see that dimensions are not the same as units. So the kilogram is not a dimension. And we can also see that dimensions are not the same as physical quantities. Physical quantities are different from dimensions. Physical quantities have dimensions, doesn't mean that they are the same. Okay, so length has dimensions. So dimensions are a whole different concept on their own. There's this separate from unit and there's this separate from physical quantity. And they were introduced because their analysis will help us solve a lot of problems. Their analysis will help us do a lot of things in science. That is why they were introduced. So they are a concept on their own. They are not the same as physical quantities and they are not the same as units. You may not understand this at this moment, but delving deeper into this course, you understand. Another thing that is also very important to note is that all these quantities are written here. I'm written 4 physical quantities, 5. 1, 2, 3, 4, 5. There's a third one, that is electric charge, are considered fundamental dimensions. Their dimensions are considered fundamental. That means that all other dimensions depend upon these 5 dimensions, upon these 5 physical quantities. Is that okay? If that is the case, then it means that we can actually express the dimensions of derived quantities using the dimensions of base quantities. And so for the next part of this video, that is what we are going to be doing. So what we are going to be doing from now on is we are going to be expressing these physical quantities in terms of their dimensions. We have the first 4 are the fundamental physical quantities, and then the rest are derived quantities. Okay, so let's begin. So the very first one, time. The dimensions of time. I want to find a dimension of time, so I need to do this to show that I want to find a dimension. The dimensions of time is t. You already know that. The dimension of length is uppercase letter L. Dimensions of mass is M. Dimensions of temperature theta. If these are the fundamental dimensions, then these are all the rest of the dimensions. The dimensions of the rest of the physical quantities are going to be a combination of these letters. So let us begin. Okay, so let's start with our first physical quantities. Let's take area. We are going to find the dimensions of area. We are going to express area in terms of its dimensions. Okay. So what is the dimension of area, or what are the dimensions of area? Okay, to be able to do that, you first need to know the formula for calculating area. Okay, so area is equal to length by breadth. The dimensions of area is given by the dimensions of length is L. The dimensions of breadth, L is also length, that is also L. So therefore, the dimensions of area is given by L squared. So if I ask you to find the dimensions of area, you can just tell me L to the power 2. So, okay, so we are going to move on to find the dimensions of all of these ones. Okay, so let's be quick about it. Okay, so we've done this one. We are picking volume. What's the dimension of volume? the dimensions of volume is what? First of all, we need to know the formula for calculating volume. So volume is given by length, breadth, and then height. So the dimensions of volume would be L times L. Height is also length. Okay. So the dimensions of volume would be L cube. Now density. Density is mass per unit volume. So the dimension of density will be the dimension of mass over the dimension of volume. So mass, we already know that is M. The volume will be L cube. So we can write this as either this or this. So this is the dimensions of density. So moving on. Now we are moving on to velocity. Velocity is distance over time. So dimension of velocity will equal to the dimension of distance or displacement over the dimension of time. This will give us distance is length, time is t. So I can either write this or I can write this. Now let's move on to acceleration. Acceleration is velocity over time. So the dimension of acceleration will be the dimension of velocity over the dimension of time. This will give us velocity is here, Lt minus 1 all over t. So this is going to be Lt minus 2. So now moving to force. Dimensions of force. What is force? So force is mass times acceleration, right? Remember, you need to know the formula. If you don't know the formula, you can't calculate. You can't find the dimensions. So it's as simple as that. So what you want to do to help yourself is that you want to familiarize yourself with all the formulas of almost all the derived quantities, especially. Okay, so that finding that dimension will be easier for you. Okay, with practice, it will become easier. You will not have to go through the whole steps of writing a formula. With practice, you get to know that it's easier. You get to recall it from memory, so things will become easier for you. So force is mass times acceleration. Therefore, the dimensions of force will be the dimensions of mass times the dimensions of acceleration. That will be m times, we've already found acceleration. If you remember correctly, it is Lt minus 2. So this is m Lt minus 2. So this is force. Now let's look at impulse. Impulse. So what is impulse? Impulse is the time effect of a force. Okay. Impulse is given by the formula for impulse is given by F times T, or change momentum. So M V minus U. Okay. Change momentum. This is momentum. Momentum for the initial velocity and final velocity. So the change in this is what we call impulse. Okay, so this is the formula for impulse. So you can either use this or this. Which one do we use? I want to use the first one. So that impulse, the dimension of impulse is equal to the dimension of force times the dimension of time. F is force. Before we do 400, it is Lm Lt minus 2 times T. So this will give us MLT minus 1. So this is the dimension of impulse. So I'm going to need pressure, momentum for you to try. Okay, you can comment your answer in the comment section below. Don't forget to like, share, and leave your comment down below.